Okay, so now we're recording. So basically, what's happening with your with combinational circuits is that it doesn't really matter what the current output of your circuit is, right? So it just takes any order or the order of the inputs or the value of the inputs at this point in time will not affect the value of the outputs later when we consider that the state of the system is the output, right? So let's say that this is your output. Sometimes it's not necessarily the case. So basically, when we have the combinational circuits, there is this existence of a feedback path that uses the current value into your combinational circuit that then predetermines where we go or what the next state is absent in combinational circuits. With sequential circuits, it is absolutely necessary that you have memory, right? Because that's like saying that I am in state A, and if I have this input and it's equal to 1, then I will go to state B. But there's a but there. But if I'm in state A and the input is equal to 1, then I will go to state C. Okay? So that's like, imagine, let's say, for example, um, mm, you're driving, let's say you're driving, and then you come to a crossroad where you can either turn right or turn left. And then depending on, let's say, the instructions that are given to you, you can either go right or go left. So, uh, yeah, depend. Yeah, so that means that if you weren't at that specific crossroad, the value of the input wouldn't be useful, right? So this process right here, where you have an input and you have your output, and um, they are being used to determine the next state. This is what, if you have time, try to look at this. This is the generalization of something that does this, something that says that the state is a function. So I'm going to call it a function of the input and the current state. When you have something like this is usually something that we call a Markov process. If you have time and if you're interested in, um, not, it's not really mathematics, this is more of, well, yeah, just representation of systems, try to look into Markov processes because this is actually quite interesting. Okay, so anyway, just a short recap of what sequential circuits are. And so one thing that we will spend time today talking about is this part right here, which is your memory or your storage elements. Remember, without the state, without some way of being able to store your current state, it would be very difficult to perform this. Which brings us to the first thing that we're going to talk about today, and that's the D latch. So what we know, okay, so let me sort of turn this around and check if you've really understood what the D latch does with. So we're talking about the D latch with the enable, right? So I'm gonna try to write down the circuit if I can remember it properly. If you have a correction for this, just say so. That's going to be D. Going to have an inverter here. And then we are going to have your NAND implementation of a D, of a RS flip-flop here. So this is basically the circuit that we're talking about, right? So you have an enable pin, and it allows you to control when the value of D will be sampled. So this is your circuit, and you can analyze that in your seats. But if I were to ask you to write down pseudocode, imagine that This D here is some variable, enable is some variable, and Q is also some variable in any programming language. And so if I were to ask you to write down C code or pseudocode for this, how would it look like? How would you write down the pseudocode for a D latch? So I'm going to delete this because we might use this for our pseudocode. I want you to sit down in your seats, think about how you would implement the logic of a D latch if it were a programming language, if we weren't using a circuit. Let's say that you're sort of simulating how a D latch works. How would you go about that? Let me check if anybody has an answer. Anyone? An array? Okay. So how would you implement your array? So we're talking about the signals here, right? So let's try to think about this. So this is sort of important because if you can explain it using pseudocode, then you really understand what the D, the enable, and the Q, or how they function in a logical sense. Not necessarily using circuits. Using circuits is how we implement them, but D latches exist even beyond circuits. The D latch or the concept of the D latch can exist in anything. It doesn't have to be in a circuit. Anyone? If the input is high, the data will be stored, and if it is low, it will be trapped. Yes, but how would you write that down as code, Mr. Owano? You've got the logic right there. That's true. That's the algorithm, shall we say? That's the worded representation of the D latch. Okay, so anyone? If and else. Yes, that's right. Of course, if and else. Exactly, right? It should be pretty straightforward. We can basically say if enable, I'm going to use C language for my implementation. If enable, then Q is equal to D, right? Else Q is equal to Q, right? Isn't this how you're going to implement this? So basically, we're just going to copy D into Q when the enable is high. Otherwise, Q is going to be Q, right? So it's going to trap the value. So whatever the value of Q is when we start up the system, then it's going to be maintained as long as enable is equal to 0, right? So to make this clearer as pseudocode, let's not follow the C convention, but instead let's really explicitly say that when enable is equal to 1, else do that, right? Okay, so does everybody understand this part, how this works? If you don't, then you're in trouble because you're third-year computer engineering students if you don't understand this. Okay, any questions so far? You have any other implementation? Anyone? Can case switch also? Yes, of course. It will also work. You can use case and a case switch here, but yeah, it only has 2 values, so you only have case and case 0 and case 1, but essentially it will be the same. So conditional statements is what we would use to implement this. Okay. Okay, so try to think about that when we continue with the other types of latches and the other types of flip-flops that we would have later. Okay, so latches are nice because they are probably the simplest um, implementation of a storage element, right? So if you actually think about it, the D latch right here, because it basically copies whatever you have at the input and stores it, is what we call the simplest implementation of memory, right? This is memory. So that would mean that if I say that my computer has 1 gigabyte of memory, when you say that, oh, my computer has 1 gigabyte memory or 1 gigabytes of memory, what you're essentially saying is that my computer has 8 billion D latches inside, right? That's what you're really saying when you're saying I have 1 gigabyte of memory, because, well, 1 byte is equal to 8 bits, and every single bit, since this can store 1 bit of information for just 1 or 0, then you have 8 D latches for 1 byte. So 1 gigabyte would mean that you have 8 billion, right? Because giga is 10 to the power 9. So yeah, just a little bit of information for you. Inside your computer, there are billions of D latches that basically function similar to how this is functioning right now. Okay, so in a lot of cases, what we use to enable your D latch is actually um, something called a clock. So the clock will give us um, a predetermined frequency of how many times we sample the value of D, right? Or how many times we get the value of D. Now, there's a reason why we want to use a clock instead of something asynchronous like an enable. And the reason for that is because a lot of the computation that we perform actually requires some kind of timing. So let's say, for example, um, let's say that you're trying to implement a sequential system, and so therefore you're using sequential circuits. A perfect example for that would be a stoplight, right? So your stoplight is basically just a circuit, and it performs a sequence. Let's say that it's going to be red for 10 seconds, and then after 10 seconds, it's going to be green for about 5 seconds, and then it's going to be orange for about 2 seconds, and then it's going to go back to being red. So that is a sequence, is it not? So that means that we need some kind of timing, right? Some kind of pulse that continuously controls how long this specific state is going to take. So that's why we use a clock. And in most cases, your clock will be a pulse. This is typical, right? So usually 50% in duty cycle. So it's going to be on for 50% of the time, and then it's going to be off for 50% of the time. This is for stability. We do use clocks for 50% duty cycle for clocks for stability. So this is also where the idea that when you say that my computer runs at about 1 gigahertz, right? So that is also where the idea of the clock frequency comes from, because when you try to process something, we usually use a sequential order, a sequential process, right? Just like your flowchart, where you have a start, you have a read, input output process, you have a process, you have an assignment, and then you have conditional statements. Now remember that every single one of those is usually implemented not instantaneously. You look at that in sequence. So that sequence is going to be executed at not necessarily equal intervals of time, but at some specific, with respect to some reference, which is the clock. So yeah, That's why your computers, when you say, I have my computer's running at 1 gigahertz, that is basically saying that the sequence that it can perform, the fastest sequence that it can perform, is clocked at about 1 gigahertz, or 1 gigahertz is 1 times 10 to the power 9 hertz, or basically it's saying that it can go through a sequence uh, about it can go through about 1 billion sequence in 1 second, right? So if you're going to say that I have a 3 gigahertz clock, then that would mean that you're saying that your system can go through 3 billion sequences in 1 second. That's basically what it's saying. Now, the problem with so we're saying that our D latch is our memory, right? And we want to use memory so that we can implement something like this sequential system. The problem here is that the idea of using an enable here when enable is equal to 1, you copy the value of Q into D, sort of becomes difficult. And we will have an example for that. So as we said earlier, sequential circuits usually take the output and then we apply it to the input for feedback, right? So now that we have our storage element, let me take the output, and for absolutely no reason other than for pure example, let me invert that so that this is now our sequential system, right? So let's sort of go back and review. This is your memory device. This is our state. We take that, we go back, and then we apply it to our combinational circuit. And we also have an input. In this case, I'm disregarding the input. We don't have an input for this system, but what we do have is the feedback path, and this is our combinational circuit, right? Because the timing doesn't matter for this one. It will just take the input and it will spit out the output almost instantaneously, right? Maybe in a femtosecond, it will spit out the value. So this is your combinational circuit, and then you're applying it to your storage element once again, your memory. So we're trying to control how fast we perform the process of copying the output, inverting that, and applying that to the input, right? So I have here a graph, something like a graphing paper, and let's try to analyze what this will do if we used a clock and we used a D-latch in our sequential circuits. So the clock, as we talked about, would probably look something like this, right? So I think that you already were introduced to timing diagrams last meeting. So timing diagrams assume that the horizontal axis that we have here is time. So sometimes this can be in milliseconds, nanoseconds, or seconds. In this case, I'm just using a standardized time. I'm not really saying anything, but I'm really much more interested in the shape of the waveform rather than the exact time in between that defines the waveform. Okay, so if this is our clock and we're using our clock as our enable, and we know that this here is how a D-latch functions, then we could naively say something like, okay, so this is going to be Q. Let me write down Q. So how can we calculate Q from this? So let's say that the initial value at time is equal to 0, which is right here. Let me write down Q at time equal to 0 is equal to 0. Okay, so I'm just going to say that by some random process, we turn on our circuit, and then the value of Q is initially 0. So I'm going to have it at 0 right here. So if Q is equal to 0, then D is going to be 1, right? D is going to be 1. So let me write down the value of D here. So D is going to be 1 right over here. Now, since D is 1, it's not going to reflect onto Q now, is it? Because enable is still at 0. So this is going to stay at 1 and D is going to stay at 0 and D is going to stay at 1. But when clock goes high, then if we look at this, when enable is equal to 1, we copy the value of D into Q. So D at the instant when we transition from 0 to 1 is equal to 1. So that means that this would become something like that, right? And then we continue. So now that Q is equal to 1, D goes back to 0. And then we continue, right? And then when we get to 0, sorry, let me delete this part. So this is going to be something like that. And then when enable goes back to low, this is going to keep that value, right? So as long as this is 1, this is going to be 0. And then when we go back to 1 again, it's going to invert the value of D again, right? So that's what we're doing. D right now is equal to 0. So it's going to copy that. So we're going to go back to low. And then we're going to get something like that, right? So we could naively basically say that this is what it would look like. This is how it would function, right? Take the value of Q. Let's invert that. Let's wait for enable to go to 1, right? You could say that. However, the truth is that this isn't really how it works. The way latches work is that as long as the enable is 1, as long as the enable is 1, we will continuously copy the value of D into Q. The only thing that we need to remember is that there is going to be a slight delay between D and Q. Okay, there's going to be a slight delay between the value of D appearing into Q, so short that it will be somewhere in the nanosecond range. So in essence, the D latch, if we try to implement a D latch using code, it's not going to be if, else, and then that's it. It will in fact be something like while 1, right? So as long, this is going to continue forever and forever and forever and forever. So as long as the enable is equal to 1, we will continuously copy the value of D into Q. But because of that slight delay, what is actually going to happen is, well, initially when this is low, this is going to be 1, right? But when enable goes to 1, first what we do is we copy the value of D. So this goes to 1, right? But when that goes to 1, D goes low. So after some time, that D that we have seen here, the D here is going to be reflected at the output of Q. So Q is once again going to transition and is going to transition and is going to transition and is going to transition because it's being inverted. And as long as the enable is high, in which case here we clearly see that that's what's happening, this will toggle back and forth. And the last value of Q will be random depending on the amount of time. So when this goes back to low, it's going to store that value. So sometimes it's going to be the case wherein, let's say it's going to look something like that. It's going to toggle back and forth, and then it's going to stay at 1 because the last value of Q was, let's say, 0. So that would mean that the last value that was seen on D, of course, this one is going to copy that. And so it's going to be something like that. But it's going to be inverted. So 0. So it's going to be something like that, right? So it's not performing what we imagined it would perform. And that's because we're using a D latch. So in a lot of the cases, what we want is we want the timing to occur not here at the level, not here when it's going to be 1. We want the transitions, or we want the copying of the value of D into Q to happen here only during transitions. It can be on the high transition or the low transition. So how do we solve this problem with D latches? So this is a problem with D latches, right? Because the way that we envisioned it would work is no longer true because we're using a D latch. So what do you think is the answer? So D latches respond to levels. So the answer is flip-flops. No, I'm sorry. Not this type of flip-flops, but flip-flops as in circuits. Okay, that wasn't as funny as I thought it would be. So flip-flops are a binary storage device that is capable of storing 1 bit of information and has a timing characteristic. Try to remember this part, timing characteristic. So it's not like the latch wherein the level of the enable is what we wait for, right? So if we go back, see here that we are waiting for when enable is equal to 1. So it's not so much about the timing with the latches, but for flip-flops, it is. So here, whereas latches are level sensitive, so either 1 or 0, flip-flops are edge sensitive. So the term that we use is active edge. So this means that we respond to either a rising or a falling edge, or a positive or negative edge. So if we go back to what a pulse looks like, if we try to expand what a pulse looks like, this is what it would basically look like, right? A single pulse. So this here would be your rising edge, or positive. And this here would be your falling edge, or the negative edge. Okay? Okay, so far, any questions? Are we clear with the difference between a flip-flop and a latch? Okay? No questions? Yes, Mr. Chia. Why? Yeah, continue. Okay. So let me go back. It's not practical for synchronous because of this reason. Because what we want is we want to be able to control the sequence in a strict manner, where we would want to use a clock, right? So the clock has 2 properties. Your clock will have 2 properties. The first one is the amplitude of your clock, how the voltage is represented. Is it 5 and 0? Is it 3.3 and 0? So on and so forth. The second one would be the frequency of your clock. Now, this one, the amplitude, can degrade. It can become, because of capacitance, what can sometimes happen is the clock can look something like this. Okay? So it degrades. Sometimes there might be cases wherein the clock would also look something like that. So what is always constant with clocks, even though their amplitude would change, is the frequency of the clock. So we want to be able to have precise timing, right? We want to be able to have precise timing when the transitions will occur. We want to be able to control that. The problem with latches is that if you use a latch here, these transitions are not part of the design. They happen because of the property of the D-latch. What we wanted was something like, what we originally wanted was that when the output would be, or when the clock would, when it would be enabled, we would copy the value of Q and invert that. So when Q would be, so what we wanted was that the output of Q would be something like that, right? So copy the value of Q. When this goes to 1, copy Q and invert that. That is what we initially wanted. But the side effect of using a latch is that we don't get this one, because the latch continuously switches back and forth because of this property right here. So sequential circuits typically will not use D latches. They will use D flip-flops, or flip-flops in general. There are other types of flip-flops. Okay, is that clear? Okay, so yeah. So yeah, that's why we don't want to use D latches, because of this unintended consequence of the D latch. And it's a property of there are applications where D latches work. But in most cases, when we try to implement a sequential circuit where timing is paramount, where timing is absolutely important, then we use D flip-flops, not D latches. Okay. So yeah, so if we were to use flip-flops, then even if our signal, or even if the clock had, let's say, some skew problems, so that it would instead look something like this, as long as the skew is symmetrical, then the timing for when we transition is always fixed. Okay, so as long as the frequency is maintained, even if the amplitude was reduced slightly, let's say it becomes smaller, or let's say it happens so that the clock looks something like a undamped signal like that, the transitions will always reflect the frequency, right? It always reflects the frequency, so we can control the frequency, whereas the amplitude is sort of difficult to control. Control in a sense that frequency isn't affected so much by noise, whereas amplitude is affected by noise a lot. So that's why we use, that's another reason why we would use a flip-flop. So flip-flops come in different types. There's a D-type, a T-type, SR, and JK. And we will go through these types today. But the first thing that we should look at is, so how do we implement a flip-flop, right? So how do we make a latch so that it responds to these things right here? Okay? So what we want instead is, instead of having the original case when we said if, and then we said enable equals 1, then Q is equal to D, else Q is equal to Q. Remember that this is, and of course, let me make that complete, while 1, because this will continue on and on. This continuously happens at lightning speed. So instead of something like this, how can we convert this so that we instead have the logic to say, if, now I'm going to use a function that indicates that I'm waiting for a rising edge on the enable. Okay, so if I were to create a pseudocode for this, I would create a function that would return a logic 1 when we have a rising edge. And then when we have the rising edge, that is when we would copy the value of D into Q. Otherwise, if there is no rising edge, if the value maintains at 1, or if it is a falling edge, then this will never happen. This is not going to happen. This is only going to be executed. The copying of the value of D into Q is only going to happen here when we have that transition. Okay, so this is what we want to do with our D flip-flop. And we implement that with two ways. The first one is with a master-slave D flip-flop. So we use D latches essentially, okay? But what happens is we have the clock, and then we have an inverter connected to the second stage of the clock. So we are using two stages of a D latch here. So this is still a latch and this is still a latch, but this time we have, well, this is essentially the master and this is the slave flip-flop, latch, I mean. So let's say that we have a clock here. This is actually quite easy to trace. So let's say that this is the value of our clock. Let's just do a couple of these clocks. So the first, now let's look at the value of Y, which is this flip-flop right here. Or first of all, let's simulate some value of D, okay? So let's say that D goes to 1 here. It's maintained at 1 there. Goes low here. And then let's, let me see. Okay. Okay. So let's say that this is our D signal, right? And so let's try to forget this part first, okay? Forget that. So let's try to focus on this part first, because this is, once again, this is something that we can do because we're using just basic latches here. So here, when clock goes to 1, we just copy the value of D into Y, right? So let's say that initially Y is equal to 0. So it's 0 here, but as long as clock is equal to 0, we keep the value of Y, right? Y is equal to Y. Then when clock goes to 1, we then copy the value of D, right? So as long as that's equal to 1, that's equal to 1, this goes back to 0. So now Y is maintained at 1. But now this is 0, and we're going back to 1. So we once again copy the value of D. So this is our Y now, right? So here, this is 0. Clock is 1, so copy the value of D. And as long as this is 1, we should be copying the value of D. So this is how it would look like, right? Okay. So now what about Q? This is when we start looking at this one. So now let's not think about this one, but now let's think about Q. One thing that we should notice is that there's an inverter here, right? So basically, the enable for this latch happens when we have a low signal. That is when we copy the value of Y into Q whenever clock is low. So if we try to okay, so first the value is going to be, I can't write. So let's just copy the value of Q for this case. So when Q is low, it's going to copy everything. I can't click on this because of whatever that's in the foreground. So let me just say that that's 0. And then when we go here, so Q is going to copy. I'm going to try to fix that later. So let's just go ahead with this part right here. So Q is going to be copied at the low portion. So that would mean that we would have a 1 here, and then that would be maintained as long as there, and then this goes low, so we copy that there. And then we maintain that value. We disregard this value because we are high when this happens. So we copy this here because it's low. And then we just continue. Okay? So notice that now what's happening is we are actually responding to the changes only to clock. No, I mean, not changes to the clock inverse, but to clock itself for Q only when we have the negative edges or the falling edges. I can't draw it right here because of what's happening there. So basically, let me clear this part. So it's going to be 0 from here all the way there because we can't copy Q unless clock is low. So we did copy Y for this portion right here, but then we have something like that, right? So we go to 1 when we have the value of clock is equal to low. So Q is 1 here, so it goes high there. Okay? So notice now that the synchronization for Q with respect to clock is happening at every single edge that we have. So this is how we would implement a D flip-flop using latches. Okay, so this is the first type. The second way that we implement a D flip-flop uses latches, but it's much more involved. Now this one, I can't write a timing diagram for this because there's too many terminals to look at. So what we will instead do is we will sort of imagine what the effect of the clock is even as D transitions in between them. Okay, so this will be a positive edge triggered clock. So that means that when the clock goes from 0 to 1, that is when the value of D is captured. Okay, so when it's 0 to 1, Q copies the value of D. Okay, let me delete that for now, and let's try to analyze this, how this works. Okay, so when clock is equal to, remember that clock looks something like this. So when clock is equal to 0, what happens to this entire circuit? When clock is equal to 0, remember that the NAND gate, the way we describe NAND gates using words is that the presence of a 0 makes 1, right? So when this is 0, automatically, without even thinking about the value here and the value here and here, we know that this is going to be 1, right? This is going to be 1. This is going to be 1. And since this is 1 and this is a latch, this is a latch, we know that this is going to be a 0. And then this is also going to be a 0, right? So remember that when this is a 1 and 1, what happens is the latch stores its state. It's not going to make any transitions, right? Okay, so what then happens when we transition, let's say right now D is equal to 0. So before I transition clock from 0 to 1, let's say that we transition D from 0 to 1. Okay, so clock is low, but we're trying to change D from 0 to 1. Is that change going to be visible here? So remember that this is already a 1. is waiting here. So even if we transition this from 0 to 1, the value here is not going to change, right? So even if you make this, if you toggle this as if it were a clock, if I make this do this, the 0 and 1 will give you 0. The 1 and 1 will still give you 0. So even if D changes right now while clock is low, this is going to be maintained. 1, 0 is going to be maintained, which means that this 0 is going to go here, and 1, 0, that's going to be a 0. And so the entire system is stable right now. Okay? So it's functioning just like a latch right now, right? So even if D changes, as long as clock is equal to 0, we don't see any changes at the output. So let me maintain that clock is equal to 0 right now. And so, yeah, that's it. But now, what happens when clock transitions from 0 towards 1? Okay? So from 0 to 1. Let's see. So this becomes 1. This becomes 1. And wait. 1. This is still going to be 0. So this is going to be 1. But notice that on this side, so this is still going to be 1. But this 1 here, this is going to be 0, 1. Press of a 0 makes 1. Oops, sorry. Wait. When we transition from 0 to 1, wait, this is going to be 1. That's going to go in there. 1 goes in there. That's a 0. Oops, sorry. This should be 1. Presence of a 0 makes 1. That's 1. Goes to 1. And 1. This is 0. Yep. Okay, so we have a 0. Yeah, so that still would be 1. Yeah, this one's quite challenging to imagine what's actually going on. So 0 to 1 here. This goes to 1. Yeah. Correct. That's right. That's right. So now this is a 1. So when this transitions from 0 to 1, this is 1 here. So that becomes 1, 1, 1. That would make this 0. Now remember that your NAND is sort of an inverted type of latch. So a 1, 0 here would force this to be 0. So this is the, we just basically copy the value of D to 0. Okay? So now that this is going to be 1 right here. So that this is 0. This is going to be 0. So that means that this is going to be 1. So now that this is a 0 and this is a 1, notice that this would now be 0, right? So as long as this is 0, even though D transitions, even though clock is 1, even though D transitions from 0 to 1, this will still remain as 1. So this will remain as 1, this will remain as 0, and so this state will be maintained as long as clock is maintained at 1. Okay? So notice now that it was only during the transition that we reflected this change here. Right now, because of this second latch, this is 3 latches, by the way. So because of the second latch, we were able to more or less store the value of the transition from 0 to 1. So we only respond when we have 0 to 1 transition. When we transition this from 1 back to 0, sorry, when we transition this from 1 back to 0, what happens is this goes back to 0. So this goes back to 1. When this goes back to 1, 1, 1 would mean that the latch maintains this value. So once again, we don't have any change. So that means that with this example, that what we just traced with the rising edge, we copied the value of D into Q. As long as the edge was high, any changes on D were not recognized. When we had the low transition, that was also not recognized because we just basically go back to the store state. Okay? So now let's sort of reset this and let's try to see what happens when we set that D is equal to 1 and we have a transition. Okay, so right now D is 1, clock is equal to 0. So once again, when clock is equal to 0, the presence of a 0 makes 1. So that becomes 1. That becomes a 1. This input right here is 1. So 1, 1. This becomes a 0. That means that this is also 0. The presence of a 0 makes 1. So that's already set. We just already set that to be 0, 0. But this is still 1 right here. This is now a 0. So the presence of a 0 here makes this a 1. That is a 1 right there. And that is a 0, making this 1. And everything is stable. So it's going to keep the same value for whatever it had previously. We are in the store state. Now, let's transition so that we have 0 going to 1. Okay, so that with this 0 to 1, that would then mean that this becomes 1. So this was initially 0. Now this has become 1. So 1, 1, this becomes a 0. This becomes a 0. So this becomes a 1. That is still the same. That's going to be 1, 1, 0. So this is 0, 1. But remember, this will be inverted. So now Q will become a logic 1 when we transition from 0 to 1. Now let's see what happens if I try to change the value of D back to a 0 here. And this is sort of different from the previous case, because now when I transition this from 1 to 0, so from 1, 1, this goes to 1, 0. So this transitions from 0 to becoming a 1. When that becomes a 1, this is still a 0 initially, so that this is now transitioning to a 1. So 0 and 1, that would still give you a 1 there. The 1 there would give you a 1 here. This is still a 1. 1, 1 would still be 0. And so 0, 0, yeah, nothing happens. It's still 0, 1. So we are still going to maintain here, even though we try to transition D after we transition clock. Now, when we go back from 0, from 1 back to 0, sorry. So when we go back from 1 back to 0, what's going to happen now is that this goes back to, from 1, 1, this goes back to 1, 0, in which case this goes to 1. And so we are in the store state. Okay, so once again, we transition from 0 to 1. thereby copying the value of D at that instance. Even though we transition D, while clock is high, it does not have any effect here. And so therefore, the clock is maintained, or the value of Q is maintained at 1. Okay, so the flip-flops are, once again, flip-flops are either implemented using this here, a master-slave flip-flop, or with this one, using SR flip-flops. So I think that the implementation is dependent on the type of circuit that you have. I do believe that a lot of circuits, actual integrated circuits, are actually implemented using this one, master-slave flip-flops, because this might require a little less gates. So you have 4 gates, you have 8 gates here. This one, oh, this one has 6 gates only. So yeah, maybe this one will also work. And it's all NAND gates in any case. So yeah. So this is how you would transform a latch to a flip-flop, in particular the D type of flip-flop. Okay, so let's try to look at the difference between a latch, a flip-flop that is has a positive edge, and a flip-flop that is a negative edge flip-flop. So we indicate that we can determine whether or not a flip-flop or a latch is either level triggered or edge triggered, whether it's a flip-flop or a latch, by looking at the value here. So notice that E here is just another input. We just recognize it as another input. But here, notice that we have this symbol. Now this one indicates that this requires an edge. So when we have this, this means that this is a positive edge triggered flip-flop. This is a D latch, D flip-flop, positive edge triggered. To indicate the negative edge, we just use a bubble in front of our edge indicator. So this is the edge and it's being inverted. So basically we're saying on the negative edge, we make the transitions. So let's try to see the difference in the outputs, given that we have this clock and we have D right here. And notice we must always take note of the transitions, okay? So this one is a falling edge. This one is a rising edge. This one is a falling edge, right? This one is a level 1. This one is 0. This one is level 1. This one is 0, okay? So let's try to plot out the value of QA, which is for the latch. Initially, we copy the value of D because clock is high. So as long as clock is high for a latch, we copy the value, right? Up to here, then clock goes low. So whatever the value of Q is, we continuously copy that. We no longer copy the value of D. So we don't copy this part. We don't copy that part either, this part. So it's always going to be 0. And then when we go to 1, we start copying the value of D, but it's just 0, so doesn't matter. Then we transition to a 1 because we are allowed to copy D because clock is 1 and we are using a latch. We still copy it up to here. We copy that up to there, up until we go back down to 0. So we chop that part. I'm sorry, mistake. So at that point, clock goes back to 0, and we just store whatever value that we had previously. So this is now just 1. Okay? For QB, remember now the sensitivity of your circuit is towards the positive edge. So whatever the value of QB is initially, we don't know. So I'm just going to assume that the value of QB at time equal to 0 is QB is equal to, let's make it 0, okay? So oops, that's going to be 0, and we're going to maintain this value because there is no rising edge. So it's going to be maintained, and then when we get here, we copy the value of D, right? So D here is 0. So this is just going to be 0 all throughout, I guess. That's quite uninteresting. So yeah, it's just going to be 0 all throughout, right? Because every single positive transition, there's only one positive transition here, and it's happening here, right here. But D is 0, so we just copy the same value. So to make this a little more interesting, let's make QB equal to 1 at time is equal to 0, okay? So that we can make this 1 in the beginning, and it doesn't change at all, not until we get here. Okay, so we have something like that, okay? For QC, once again, let's assume that at time equal to 0, QC is equal to 1. So let's assume that this is a 1 here. Now I'm waiting for the transition from 1 to 0 for QC because it's negative edge triggered. So now I see that D is equal to 0, so we copy the value of D here. But notice that afterwards, we don't have any other clock, so this will just maintain at 0. We have no other falling edge, so we wait until we get to here. So now that we have the falling edge, we look at D, and D is 1 here right before the falling edge, so we have that logic 1 here, and then that is maintained as such. Okay? Okay, so this is how edge-triggered flip-flops work, right? Now, once again, the nice thing about edge-triggered flip-flops is that the timing is sort of strict, okay? So there is, however, something that I'd like to discuss that is much more sort of a practical property of your D-latch. So your D-latch has something called a setup time. So the setup time is a minimum amount of time for the value of D. So notice that when the falling edge happens here, I always said the value of D here, right? Just right before the edge. Because of the way circuits work, there is a minimum time that the value of D has to be stable. And whatever that time is, that D is stable, the value of D at that time will be sampled when we have the transition. So this will be a very short time, but it will be finite. It's not 0, right? So this time, the setup time is not 0. So there is a minimum time. Now that it depends on the manufacturer. It depends on the type of technology that's used. If it's low power Schottky, or if it's CMOS, if it's high speed CMOS, these things change. So you need to look at that using data sheets and data books. And most manufacturers will write that down. So yeah, this is quite important, okay? So when the edge happens, what we will be looking at is not the actual value of D at that very instant. it will be more or less the averaged value right before that clock. But this will be a very short period of time, maybe once again in the range of nanoseconds. So maybe 2-3 nanoseconds before the clock, that is going to be the value of D. Now, there is also something called hold time, and that is also the value of D, the value of D that it is held right after the clock. We must ensure that the value of D does not change for that specific time. Now, so it's relative to the edge of your clock. If we're looking at the falling edge, setup time is the minimum time that D is constant before the edge, and hold time is the minimum time that D is constant after the edge. Okay, so let's say that this is your edge. When we're looking at the falling edge, that would mean that there is a minimum signal or length of the signal. So setup time would be this time right here, whereas hold time would be this time after the clock. Okay, so if we had a pulse that was too short, let's say that looked something like this, then there is no guarantee that this one will be sampled by the D flip-flop. Okay, because of the length of the pulse, it's too short, we can't guarantee that it will be sampled. Okay, so that's a practical sort of shall we say property of a flip-flop. It's not instantaneous, wherein no matter how small this time is, the pulse time is, as long as the edge trigger comes, then we should be able to sample this value at this very instant. No, it's not like that. There is a minimum time. So there is a minimum length of a pulse that you can sample when we're talking about flip-flops. Okay? Okay, so far, any questions? Yes, to your question, Mr. Chia, in this case, in the case of this circuit that we have, yes, we do make the transitions on the negative edge for this one. For this one, it's going to be on the positive edge. But there is a way that we can make this positive edge. We can make the master-slave flip-flop positive edge, and that's by moving this here. If we put an inverter first, and then we connect that there, and then we take the inverter, and we just, so disregard that, and we connect it like this, then it becomes positive edge triggered. Okay? But otherwise, yeah, it is negative. This case, it is negative edge triggered. Okay, so there are other types of the flip-flops. Now, it depends on the functionality that you want. So some circuits or some D flip-flops have something called asynchronous enable. And I'm not going to make this too difficult, but basically asynchronous enable overrides the value of D. So that when it is 1, regardless of the value of D, notice that when this is 1, regardless of the value of D, sorry, when this is 0, no, when this is 1, regardless of the value of D, the Q next will be enable and clock. Yeah, so when the enable is set, it will allow the D latch to sample the value of D. Okay, so you can look at this circuit if you like, but yeah, we're sort of running out of time. So when clock is 0, once again, this is an edge triggered flip-flop. It doesn't matter. Q next will always be equal to Q, or after the transition, the next value of Q will still be equal to Q. As long as it's 0, as long as it's 1, it's going to copy everything. So this part right here is trivial. Let's focus on the rising edge. So when the rising edge is going to happen and enable is equal to 0, regardless of the value of D, the Q is still going to, the Q next is going to copy the value of Q. So it's like a second layer of enable for your D, but it actually depends on the clock. It waits for the transitions. It doesn't override the value directly, asynchronously. So when enable, as long as enable is equal to 0, D is irrelevant. Q will still be copied back to itself. Whereas when you have a clock and enable is 1, then the value of Q next will copy the value of D. Okay? So it's like saying that as long as Q as enable is equal to 0, the flip-flop will just maintain its state. So when it's 0, notice that the next value just copies this. But when it's 1, the next value copies the value of D. Okay? So it's just a second layer of enables. Now there's another type of D flip-flop, and this is much more common. And it's D flip-flop with asynchronous inputs. So asynchronous inputs are a way of sort of enabling an initialization of the flip-flop. So something that might have been discussed earlier is that when you turn on the flip-flops or latches in general, the value of Q and Q bar is sort of random. It depends on which one of these two goes to 0 first, right? So when this would go to 0 first, it would automatically say that this is 1, so that this would then become 0. Okay? It maintains that. So to ensure that when, let's say when your system starts up, everything is either, all the outputs of the latches are either 1 or they're all equal to 0, we use asynchronous inputs. So for latches, it's actually quite simple. We just add a third input to the latch, right? Because once again, the presence of a 0 will make this 1, right? So if we bypass the enable and the D and we go directly to the second stage of the latch and we give a 0 here, this 0 will automatically make this 1, right? So this will make it 1. And so as long as this is held to 1, the clear is held to 1, then yeah, these will be 1 and that's 1. So that's 1 and 1. This will be 0. So that will be maintained at 1. And this will always be 0. Okay? The opposite of that would be to bring this back to 1. And so let's say that initially the value is equal to 1, 0, and we want to clear the signal. So the clear works by bringing this down to 0. If we bring this down to 0, this is automatically a 1, which would send a 1 waiting here. And we know that regardless of the value here, or of if enable is equal to 0, then this will be equal to 1, and preset is just equal to 1. So this will become 0. Okay? So we don't wait for the enable or the D latch when we use the preset and the clear. The only problem here really is when we make both preset and clock equal to 0, then we have the possibility of making this a 1 and making this a 1 as well, which is undefined supposedly. But yeah, you do have that capability, but you don't really use that. You either set or clear the output of your latch. Okay, so this is how we represent a D latch with a preset and clear. Notice that these are inverted. So yeah, that is an indication that a 0 would make that equal to a 0 at the preset would make this 1, and a 0 at clear would make this Q equal to 0. We can do the same thing with the D flip-flop, where we add preset and clear to the D flip-flop, but this time we don't do it to just the final stage, because we these are asynchronous, so we also need to make sure that the inputs here would become 1, right? We want these to be 1 and 1 so that we prepare for, yeah. So we want this to be 1, so wait, no, sorry. So when preset is now low, this would give us a 0 here, which would make this 1 there. We have a 0 here. This would make it 1 there. And so regardless of the value here, this is 1. That goes in there. 1. Let's say that clock, if clock is 0, then this would be 1. If clock is 1, it doesn't matter. This will still be 1. Yeah, this will be 1 for all cases. So once we bring back preset to low, then it would still be just 1, 1 anyway. So yeah, that's just basically how it works. We override the flip-flops, or we override the latches with these asynchronous inputs that don't necessarily wait for the clock signal. Okay? Okay. So there are other types of flip-flops. It isn't just the D flip-flop. And it depends on your application as to what type of flip-flop you will use. So if there is a D flip-flop, then naturally there should be an SR flip-flop or a set reset flip-flop. And we implement a set reset flip-flop pretty much the same way that we would implement a D flip-flop, right, with master-slave flip-flops. So once again, we have the master-slave here, but now we are using SR flip-flops instead. So the effect of this is that we wait for the transitions to happen at the input of the clock, right? So let's say when SR are S and R are both 0, then we get there should be an enable here. But anyway, let's not dabble too much on the internals here, because I think that you can, we've already shown how we can trace this. But what we will do is we'll just look at this table right here. So this is sort of like a combinational circuit table, wherein if we know that S is equal to 0, R is equal to 0, and Q is equal to 0, then when the clock will come, the Q next, the value of Q, will be just 0, right? So 0 and 0 on the set and reset will just copy the value of Q. So and an SR is 0 and Q is 1. When the clock comes, we just copy the value of Q. When S is 0, R is 1, and Q is equal to 0, we should be forcing the value of Q to go to 0. And we can see that, let me highlight this, 0, 1, and notice here that in both cases, 0 goes to 0, 1 goes to 0. So we are forcing it to go to 0, regardless of the value of Q. Now, when this is 1 and then this is 0, and Q is equal to 0, then once again, the clock comes, we force Q next to become 1, because S is 1 and R is equal to 0, right? And S is 1 and 0, Q, and if Q is equal to 1, then when the clock comes, Q just becomes 1. So once again, we're forcing it to become 1 in this case. Now this is the indeterminate state, which we don't necessarily know what's going to happen. And this is the same case here for the D or for the SR flip-flop. We can't know the next value of Q next. It depends on which one goes back to um, first. So yeah, just the same problem that we used to have with the SR latch. It's still present with the SR flip-flop, even though we have edge triggering now. It's really because of the fact that your inputs here on the second stage would then transition from being 0, 0, which is already an unknown state. We can't transition from 0, 0 to 1, 1 exactly at exactly the same time. But there will be cases where this will go from 0, and then it will go to, this one will go to 1 first, right? So we would then have 0, 0, 1, 0, and then 1, 1, in which case this will become 1. But there may be cases where this will go to 0, or this will go to 1 first, so that will be 0, 0, 0, 1, in which case this will become 0, and then we go to 1, 1, and it gets stored. So we can't know the states here for the SR flip-flop. And so, yeah, still the same case. SR flip-flops are sometimes useful because they require the least number of gates. So the other type of flip-flop is the JK flip-flop. Now the JK flip-flop solves the problem that we had with the indeterminate state of the SR flip-flop. So the JK flip-flop is exactly the same from here to here for the SR flip-flop. Where it differs is when we have both inputs at 1. So now, what happens is when both inputs are 1, we complement the output. Okay? So notice that when this is 1, 1, and the current value of Q is 0, when the clock comes, Q next is inverted from the value of Q. So when it's 0, it becomes 1. 1, 1, the clock comes, and Q is equal to 1, then your Q next becomes 0. Okay? Then lastly, we have the T flip-flop. So the T flip-flop is also a special case of the JK flip-flop. It happens when you short out the values of J and K. So notice that J and K here have this connection. Well, it's practically the same. This is your K, and then this is your J, and you're just shorting these out, right? So it's like saying that we're picking the states wherein J and K are the same. So that means this state right here when J and K are the same, and this state right here, okay? So what does that give us? When T is equal to 0 and Q right now is equal to 0, when the clock comes, Q next just copies the value of Q. So once again, when T is equal to 0, Q is equal to 1, the transition comes, it just copies the value of Q. But now, when T is equal to 1 and the transition comes, the Q next is the inverted value. So it's inverted for the next value of Q. Okay? So that's the main difference between the T flip-flop and the JK flip-flop. But of course, the T flip-flop is just a special case of the T flip-flop. And it happens when we short out both inputs of the JK flip-flop. Okay, so all these types of flip-flops, they can be described using characteristic tables. Sort of the same way that we describe combinational circuits using not state tables, but truth tables, we describe flip-flops using characteristic tables. So your characteristic tables are composed of basically JK, or the inputs, or the different possible values of the inputs. But notice now that we are using a term called qt plus 1. And this means the value of q after the transition, after the trigger. Okay, so the trigger that we're talking about is the edge that we want. So it could be the positive edge or the negative edge. So qt plus 1 is after the trigger, qt is before the trigger. Okay, so this is for the JK flip-flop, it's basically saying that when it's 0, 0, when both inputs are 0, 0, in qt, qt plus 1 basically copies qt. And then when it's 0, 1, we are at the set state. So qt plus 1, regardless of the value of qt, becomes 0. When we have 1, 0, qt plus 1 becomes 1 after the transition, regardless of the value of qt. Then when j and k are both equal to 1, qt plus 1 is equal to qt inverted, right? Or the complement. We can do the same for the SR flip-flop. 0, 0 would give you just the same value. There's no change. It stores the value. 0, 1 would then give us qt plus 1 is equal to 0, or the reset state. And 1, 0 for SR would give us the set state. 1, 1 is undefined. It's indeterminate. The D flip-flop, once again, pretty much the same thing as the SR or the JK, but when S and R are inverted with each other, right? So when D is equal to 0, when the clock comes, QT just becomes 0. When D is equal to 1, the clock comes, QT is equal to 1. Otherwise, it is always in the no change state. Okay? Okay. So T flip-flops, when T is equal to 0, then there is no change. QT plus 1 is equal to QT. When T is equal to 1, QT plus 1 is equal to Q bar of T, or it complements itself. So characteristic tables, once again, it's what we use to define what a flip-flop does. Okay, so the next thing that we need to talk about are characteristic equations. Now, characteristic equations are sort of like logic functions or algebraic functions or algebraic expressions that tell us how qt plus 1 happens, or how qt plus 1 is related to qt and j and k. So to develop the characteristic equation, we need to write down j, k, and q and assume that q is one of the inputs, right? And this is pretty much valid because if you remember, we said that we have a combinational circuit attached to a storage device, and then the output of the storage device is applied to the input, and we have a different set of inputs. So to get the characteristic equation, we really need this part right here. We need the signal right here. So we can determine that by taking the output, right, or the state, and applying that as an input to this combinational circuit. So we are basically looking for the algebraic expression or the logic function of this part of the circuit, not this part necessarily. So that's why we are treating Q as if it were one of the inputs to your combinational circuit. Okay, so 0, 0, 0. What happens when we have 0, 0, and Q is equal to 0? We know that when it's 0, 0, we just copy the value of qt, and that will be qt plus 1. So this will be 0, 0, 0, and 1. This becomes 1, right? Because we copy qt from q. Then we have 0, 1, 0. So when J, we are now looking at 0, 1 here. And when Q is equal to 0, regardless of the value of Q, we set Qt plus 1 to be equal to 0, right? Just as we see here. So when this is 0, 1, and then this is 1, this is still going to be 0, 1 over here. So this is still going to be 0. So 0, 0, 0, 1, 0, 1. So this will be 0, 0, 1. So now we're looking at this part right here. Remember, regardless of the value of Q, this one will become a 1, so that this 1, 0, 1 will still be a 1, regardless of the value of Q. And then 1, 1, 0. So we are now looking at this part. So now we need to look at Q, right? So 1, 1, 0. This will be, what is this? This is going to be 1, right? Because we need to complement the value of Q. And then 1, 1, 1. This will become 0. Okay, so that would then mean that Qt plus 1, or our characteristic equation, is made up of the minterms of, or the expressions that we have here, which we can write down as J bar, K bar, Q plus J, K bar, and Q bar. And then we have J, K bar, and then Q, right? And then lastly, we have J, K, Q bar. K, Q bar. So can we simplify this? Yep. Looking at this, I can see that JK and JK right here would then, we can take out Q so that this would become J, K, Q plus JK, Q bar plus this one is JK bar, Q bar plus Q. Is this correct? That's 1, 0, so that's 1, 1, 0, 1, 1, 1. One, 1, that's 0, so that becomes 1, 1, 1, 1, that becomes 0. Yep. So this becomes 1, JK bar. How about this one? JK bar. So we should, I think we can further simplify this because I know the logic function, but I can't see the simplification from this towards the end. Let me see. J bar K bar Q plus J K Q bar and then J, K bar. Uh-huh. So I can't simplify this right now directly using algebraic functions. So can we use a K-map for this so that it will be easier to solve? J bar, K bar, Q bar. JK bar Q. JK Q bar. Yeah. I'm stuck with this right now, so might as well use a K-map, right? So let's try using a K-map instead. That's going to be JK and then Q. So according to this, we have 0, 0, and then 1. Then we have 1, 0, 0, 1, 0, 1. And then we have 1, 1, and then 0. I still end up with 3. That's going to be 1, 2, 3. Zero, 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 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1. 1, 1, 0, 1, 1, 1, 1, 0. I guess this is it. I guess this is the logic function, but I believe that we can still further simplify this. I just can't see it. Anyone has an idea how to simplify this? J bar K bar Q. J K bar Q bar J K bar Q. let me try to take out J bar Q. Q bar, so then we have K right there. So that this becomes J Q bar K. So this is K bar. J K bar Q plus J K. Hey, I'll just go back to this later. So you're running out of time. Okay, so characteristic equations. Don't worry, I'll give you some supplement. I'll try to solve this and I'll supplement this video with another video later with the solved values, because I don't think that this is the final equation. It's too complicated. I remember the circuit being so much simpler, maybe only having a few gates. This one has 3 terms, and there should only be 2 terms. So I'll try to solve this, and then I'll send you a video for the correct answer for this. So the other thing that we need to learn regarding sequential circuits, and in particular flip-flops, is state diagrams. So state diagrams are a pictographic representation of the behavior of a system. Now, in this case, we're particularly talking about sequential circuits. So it shows how states transition in relation to each other and the inputs. So it's sort of like flowcharts, but for flip-flops and for sequential systems. State diagrams are actually applicable to a lot of other things. A lot of software engineers do use state diagrams to define what their software does, because your software does have states, right? So let's say, for example, you might be in the state wherein you're asking for user input, and then after user input, you might go to another state that depends on the user input itself. So basically, you can define very complicated software using state diagrams, and state diagrams are actually quite important in my opinion, because I also use this a lot in whenever we try to develop control for robotics. So in that sense, the state of the robot and the state of the inputs would then determine how the program proceeds, or what the robot does later. So they are a very important way of representing something that has a sequence, not just sequential circuits. But to define that, we always have a state, and then we have the transitions, and the transitions are represented by arrows. Now, to define how the transitions happen, we write down the state of the inputs, or the value of the inputs, and the value of the outputs when we make those transitions, okay? So let's say, for example, we have our set reset flip-flop, and we want to make a state diagram for our set reset flip-flop. So the state of a flip-flop is determined by its output Q. So remember that you only have 2 possible outputs for your set reset flip-flop. So that would mean that one state would be 0, and the other state would be state 1, okay? Now, the transitions are already found inside your characteristic table right here. So remember that when S and R are your inputs. So when S and R are 0, we just stay in the same state. So we write that down in state diagram form by saying that we are in state 0, and when SR, both S and R are equal to 0, so 0, 0. Just for this example, I will write SR here and equal to 0. But in most cases, we just say we represent that the most significant bit would be S, the least significant bit would be R, and just write down 0, 0, right? So when we're at 0 and the value of SR is 0, 0, even though we get a trigger, we transition back to ourselves. There is no change in the state. And this is how we represent that. But remember that this is also applicable when we are in state number 1. So when we are at state 1 and SR is equal to 0, 0, we just go back to ourselves. Now, when we are in state 0 and SR is equal to 0, that will bring us back to state 0. And that is when we start at state 0 and SR is equal to 0, 1, because we are at the clear state. But this is not the case when we are in state 1. When we are in state 1 and SR is equal to 0, 1, we transition from the first state, from state 1 to state 0. That happens when SR is equal to 0, 1, right? So 0, 0, 0, 0, 0, 0, 0, 1, 0, 1. We've looked at these two. Now let's look at 1, 0. So when we are at 1, 0 and we are at state, let's say 0, we know that we go to state 1. So that means that there is a transition from state 0 to state 1 when SR is equal to 1, 0. But that's not the only transition that we can have when SR is equal to 1, 0. You also have the case where you start at 1 and you go back to state 1 when SR is equal to 1, 0. Okay, so there is the last state, and that's SR is equal to 1, 1. But because we don't know what's going to happen with Q t plus 1, we can't represent that in our state diagram. So yeah, this is basically the state diagram for a SR flip-flop. Okay? Okay, so any questions regarding state equations and state diagrams? Regarding this, the JK flip-flop, I will supplement this with another video of me solving this. Maybe I made a mistake somewhere over here, but the process is basically you represent the current state as one of the inputs, and you just look for the truth table, and you look for the logic expression for that, or the function, logic function for that, and that should give you Qt plus 1. That's the characteristic equation. Okay. So we're supposed to have an exercise, but given the time, I'll probably give this as what do you think? Do you want to do an exercise, or would you rather have an assignment? Let's have a vote. Yeah, I thought of that, Mr. Mendoza. I thought that it could be the De Morgan's theorem, but I'll have to verify that. It is a possibility. That's why I tried to take it out of the equation. I'll check that later. Yeah, probably. So would you rather have an exercise right now, or would you rather have an assignment? Okay, so let's have an assignment, and then we can just continue. So I will send a assignment for you to do this. Okay. More na choices. Okay, so what other choices would you like to have, Mr. Achia, aside from assignment and exercise? No assignment and no exercise? No submission assignment. Hmm. Hmm. No, it's tempting to have that. Something with a long deadline though. Bonus for exam. I wish I could. Actually, the way you guys are doing with the lectures and the assignments, I think that most of you are ready for the exam. You should be able to get the exam quite well. So I'll try to figure something out so that it won't be too much of a workload. If ever we'll have an exercise, it will probably just be one or two, and it won't be too complicated. Okay? So I'll just send an announcement on Canvas, and as well as open up, if ever I will ask for submissions, I will open up a submissions page, or maybe not. Okay? Just wait for an announcement. Okay, so this is where we will end the class today. Thank you for joining this synchronous session.